Just hopping on to do some of our Unit 4 notes. So Unit 4 is all about chemical reactions. So hopefully a lot of this is stuff you already know. So, as usual, the notes are just to help you. So I just kind of want us to have this shared background. So that's why I'm bothering, recording this, giving you like a lecture on this. But, if you want to go through and try the practice problems that are part of the notes, and if you're able to do them on your own, then maybe you don't need to watch this. But, play by ear, whatever you need, or you can just follow along with me. Whatever will serve you best. It's up to you. So I messed with the order of the sections because I think it makes more sense the way that I have it ordered. So first thing I think we should talk about is what is a chemical change versus a physical change. So again, hopefully this sounds kind of familiar, but a physical change, this is some kind of process where there's no change in chemical composition. So it should be the same substance, but maybe the substance has different physical properties. Maybe it's spread out a different way, maybe it behaves slightly differently, but it should be the same substance, even after the process. Generally, these are reversible. Something like that. So something that changes the shape of one, like chopping a piece of wood. It is still wood. Maybe you just have two sticks now instead of one big stick. That's kind of an example of physical change. The super common one that hopefully at this point you've heard plenty of times, but just to be super duper clear, a key one that is good to keep straight is that any phase change, so solid, liquid, gas, going between those guys, any of that is an example of a physical change. We boil water, it becomes water vapor, it's still water. It is only a physical change. So the thing that is actually being changed when I do a phase change, I'm breaking IMFs. I'm not actually breaking any chemical bonds. It's still the same substance. Let's check out versus chemical. The real key here is that a new substance, often with new chemical properties, is formed. So the key part of like how I form a new thing, how I change what my starting material is that we're actually going to be breaking chemical bonds. And for our purposes, like this is pretty much like we're always going to be, I guess I'll just say chemical bonds, like we could be changing ionic stuff or changing covalent stuff. Chemical bonds, intramolecular forces are broken or formed. So hopefully it'll be pretty straightforward to keep those separate in your mind. Just to point out one that we've talked about a bit at this point, dissociation. We've talked about this before. It's like when you take an ionic thing, so like say salt, and it's like some kind of solid crystal structure, but then you pop it in water or some kind of solvent, and suddenly it breaks into its ions in the solution. Just to clarify, like, this is a hot debated subject, whether this is a chemical change or a physical change. Personally, I'm club, this is a physical change. But it's kind of like a middle ground. So I just wanted to point it out because it is a middle ground. They won't really, like, they're not going to ask you to ID it one way or the other. But some people argue it's a chemical change because like we went from having the solid to the ions, and the ions and the solid are going to have completely different properties, you know, the conductivity, stuff like that we've talked about a bunch. People like me would argue it's only a physical change because it's still the exact same substance. It's still those two ions. The two ions have just broken apart. We're not actually making a new material. So, debatable. But just to point that out, again, like being able to call it one way or another doesn't really matter. But just to kind of point that out as a weird middle ground. Okay, there's lots of signs of a chemical reaction. You're not necessarily going to have all of these. Sometimes you might not even see any of these, but if I'm making observations in a lab and I want to be like, I think a chemical reaction just happened, here's a few key things that we might see. An unexpected color change. So not just like when we did our lab and you dissolved blue dye in water and it turned blue. Not a chemical sign of a chemical change, right? Like expected color change. Like of course it was blue. But if suddenly it turns yellow out of nowhere, perhaps a chemical change. Formation of a precipitate. So again, hopefully these sound familiar already. We'll work more with precipitates later, but that means that we made some kind of solid. Again, not just a phase change, not just something I already had becoming a solid, a whole new substance that is a solid, a precipitate. We might see the formation of a gas. Again, not just something boiling, but the formation of a new gas spontaneously. Fizzing, bubbling, that kind of stuff. Another big one is a change in energy. So what does that actually look like? There's lots of things you could observe, but maybe it feels hot or it feels cold on the outside. A change, okay. Change in temp. Maybe you look at a fire and the fire is like bright and lighting up and crackling. Maybe you see light, photons being emitted. Maybe electricity. Okay. Electricity. I'm really tired. Just ignore me. Pretend that's spelled right. I do not care. Some kind of change in energy that can come in all those different forms. Okay, cool. So again, this should feel pretty familiar, but let's look at an example. What happens when water changes from a liquid to a vapor? So again, alarm bells in your head. If it is a phase change, is the same substance, we're just going H2O and making it into a gas. Same substance, no change. A physical change. So there are only going to be a change in intermolecular forces. You're not going to be breaking any actual bonds. It should still be water on both sides of your reaction. So pause it, try it. You should be able to answer this one. And hopefully we're all in agreement that the only thing that is changing in between our molecules is they're spreading out and we're breaking those hydrogen bonds, the specific IMFs in between. We're not breaking the covalent bonds, and obviously there's no ionic bonds in water. Again, pause, try the next one, see what you're thinking. So we're asked to figure out what experimental evidence we have for a chemical change taking place. So we gotta work with the data we have. It's not describing what it looks like. It's not describing energy. All the data we're given is this. So can we use these numbers we're actually given to figure this out? So what I'm noticing with these numbers is before my reaction happened, I have this mass, and after my reaction happens, I have this mass. I'll reiterate this later, but we're seeing an increase in mass. And a concept that we'll write down again later, but hopefully we feel familiar with, is that mass cannot be created or destroyed. So this doesn't just mean that like it's not just that magnesium suddenly weighs more because magnesium weighs more now. If suddenly there's a change in mass, that must mean our matter changed. My actual substance must have changed somehow. So this data is telling me that therefore there must be a new substance, a new chemical formed, which means that there is a chemical change. Cool. Okay. So reactions. What is a reaction? How do we deal with them? Again, hopefully this feels very familiar already. Just gonna point out that naming starts to like actually come up more this unit, like being able to be like sodium chloride, and you'll know what that means. Again, it's very like if you like simply don't have like I'm not gonna quiz you on naming. Just I don't think it's worth our time right now. Given the schedule. But it will make you much more confident and fast and thorough on doing AP style questions if you feel confident about your naming rules. So whenever you have the opportunity, please look back at those rules that are in the Unit 2 notes for you. Work on memorizing as many rules as you can. It's very rare that there's a question you couldn't like figure out without knowing the rules, but again, it's important. It like helps you be more fluent in the language of chemistry. It helps you be better at doing these problems. So something that can definitely help you succeed if you are able to dedicate some time to it. So we already talked about this. What is a chemical reaction? It is the breaking or forming of chemical bonds in order to make new substances with new chemical properties. And there's different ways we communicate things about a chemical reaction. There's a bunch of different symbols that we might use. So like, here's something that we should know. A classic like setup you might see is some stuff on a left side and then an arrow and then some stuff on the right side. The stuff on the left side is always called the reactants. And the stuff on the right side is always called the products. And if you see an arrow like this, just straight across arrow, it's called a chemical reaction arrow. And if it's just a straight across arrow, it's indicating that there is an irreversible chemical reaction. So it is indicating that a reaction has occurred. Actually, we do use the arrows for like physical reactions too, but it's showing that we had this movement from this thing to this thing, like a one-way little situation. You might have not seen this one before. We will spend a lot more time with it in a few units. So if I draw an arrow like this with a back and forth, this is representing a reversible reaction. One way we might refer to that is in a reaction that is in equilibrium. We have a whole unit on that, so we'll spend plenty more time with it later. But just so you know, we might have a reaction that goes back and forth from the products, and then the products go back, and then the reactions go back and forth. There's a few different things we could put on top of our arrows to represent like how this reaction gets started. If you ever see a triangle over your arrow, that is referring to heat being added. I'm going to say to initiate a reaction. So it's not necessarily a product or a reactant, but that we had to add some kind of heat to get it going. Like if you spark a match before you start a fire, you could represent that you had to like start it with a bit of energy by putting a triangle over your arrow. Don't think I've seen this much in AP stuff. If you ever see that over an arrow, it means that light, aka photons, are initiating your reaction. If we have a catalyst over the arrow, I'll explain catalyst more next unit. It's a thing that can help kind of get a reaction going. It's going to be some chemical. So if you saw like an ionic compound just written above the arrow instead of as a product or a reactant, it might be indicating that that thing is a catalyst. We'll deal with that next unit, but whatever is written above the arrow is helping the reaction go. Okay, what else might you see? Hopefully you've seen these guys before. We can indicate the state of matter of our substance with these. So if it's a gas, then you do a little G in parentheses. If it's solid, you do an S in parentheses. If it's liquid, you do an L in parentheses. And if it's aqueous, you got an AQ. Just to so we're all super clear, if it says aqueous, like aqua, that just means dissolved in water. So if you see a bunch of things that are aqueous, you have a bunch of soluble salts that are surrounded with water. So think back to last unit, like how we would draw that. What does it mean to be aqueous? What does it mean to be soluble? Upon occasion, you'll see RT. That just means room temperature. And as we're drawing our equations, we'll always be representing our chemicals with their formulas in our reactions. But you might see two different types of numbers as a part of a reaction. If there is a big number in front, it is called a coefficient. It represents the number of moles of the compound in the balanced reaction. Reaction equation. Sometimes, or hopefully, again, we've practiced this a good amount at this point, but if you see a little number, those are called the subscripts. And it represents the number of atoms per molecule. So in one H2O, there are 2 hydrogens. There's a 2 hydrogen to 1 water mole ratio. The 2 in the front would indicate that there's 2 of the water molecules, that whole thing. And we'll do some stoic practice in a sec to see how we actually utilize that. Okay, again, this is the kind of thing that could be fair game. Being able to translate words, so knowing all those naming rules, and being able to represent the reaction as formulas, as chemical formulas from reading their names. Again, you're taking a risk if you don't memorize all the naming. It could come up. There are a lot of ways to get around it. You'll see, like if this was a multiple choice question, you probably could use process of elimination to figure it out. But again, very good skill that'll help you a lot if you are able to get it down. So I'm just going to kind of read through this. What is this communicating to me? Solid nickel. So it just says nickel, so I would look up nickel. And it's solid, so I communicate that with a little s. Reacts with, so plus aqueous lead 2 nitrate. Whenever you see a Roman numeral, that is indicating the charge of the metal. So I have a 2 plus lead, and I have nitrate, which is NO3 minus. So my compound here would be PbNO3. And I would need 2 of those to have a proper compound, and it would be aqueous. Produce, so indicating that I'm going to make some products, other side of my arrow. An aqueous solution of nickel 2 nitrate. So again, you have nickel, and that nickel has a +2 charge because there's 2 in the name. Nitrate, which has a -1 charge, so I need 2 of them to make a balanced compound, and that is aqueous. And my other product, it says and solid lead. So Pb solid. Okay, so just to remind you of those naming rules and that being able to translate one way or the other is an important skill. We could represent a physical process with an equation like this. I already wrote this up earlier, but I could say I was melting a cube of ice, and I took my solid ice, and I heated it up, and it became liquid water. So the way it is, we're using kind of a similar language as our chemical reactions. We have an arrow, we have compounds on both sides of the arrows, we have phase symbols, these guys, phase symbols, states of matter. But the way I would know for sure, okay, wait, this is just a physical reaction, not a chemical reaction, is because I have the exact same substance on both sides. I've not made any new materials. I've only changed the states. Okay. Law of conservation. This is a big thing if I want to represent how a reaction happens. Like I mentioned earlier, law of conservation, this comes up all the time for chem, is the concept that, and if I'm talking about mass specifically, concept is mass cannot be created or destroyed it can only change forms. So what this means as I'm writing my reactions is that you must have same number of moles, same number of atoms, of all atoms, of all substances. Yeah, I'll say atoms, I guess. Just get down to the root of it. So, should be pretty, this should be something we already feel comfortable with. Just because my nickel is now a part of a new thing, it's changed forms, I still have one nickel. Still have nickel on one side and nickel on the other. Nickel didn't just disappear. No atoms were actually destroyed. They are just changing chemicals. They're making new bonds. There's a lot of different strategies for balancing a chemical equation. What we mean by balancing is making our equation obey the law of conservation of mass. So looking at this guy, I could already count. I have one nickel, one lead, 2 nitrates. Everything already matches on the 2 sides of the arrows. So sometimes I get lucky. This one's already balanced. But what I mean by balancing is sometimes we need to mess with the equation a bit to make it obey the law. There's lots of different strategies. So like if the way I do it doesn't work for you, there's lots of different ways you could choose to approach it and find one that works for you. the general, like I'm not going to go through it step by step because hopefully this is something we've already practiced. But the way I do it is to count the number of atoms on both sides of the equation. And a note, if you have polyatomic ions, on both sides, you can just kind of treat it as a unit. So like up here, if I was to want to check my balancing, instead of counting nitrogen and oxygen separately, I would just count that I have nitrates, just because it makes it easier to keep track of things. And a polyatomic thing is a unit with all those chemical bonds, or those covalent bonds really set in stone. So hopefully they're going to stick to, if they're sticking together, then they're going to have the same ratio already. You don't have to worry about counting the atoms individually. And if you count up both sides and they do not match, what you will have to do is add coefficients, those numbers in front. In front of species. So I think it makes more sense with an example, but just only coefficients. Once you figure out, like, okay, like this reaction, it's nickel and it's lead nitrate and it's nickel nitrate and it's lead. Those are the species, those are the products and the reactants. I can't actually change my chemical formula because that would completely change like what I'm producing. It would change what my product is. I can only add coefficients as a part of that balancing process. Just ahead of things, a few notes that might be helpful for you in the future as you're doing these. If you ever have an atom in more than one place, balance that last. So what I mean, like if you have oxygen in both products, don't try to balance oxygen first. Balance all your other atoms and then worrying about oxygen, because it'll just be harder to try to do oxygen first. Another tip, often you'll get kind of stuck with like odd and even stuff. And like you can't get the number of atoms on one side to match the other. Try multiplying everything by 2. So just double everything, and that will usually fix it for you. Again, it takes practice. It takes actually seeing some examples to feel more confident in this. But this is kind of your fail-safe. A lot of people get stuck when they can't get the odds and the evens to line up, when they can't get the things to match. So just like keep going. If you're on the right track, just keep going. Make the numbers even bigger if you have to. One little thing to keep in mind here. In order to be able to balance your equation, you need to have the right products and reactants. Like, I have to make sure that this is what I'm putting in, this is what I'm getting out. So if you ever go to try to balance something and it's really not, like, it like literally is impossible to do, and you're super stuck, always double check that your reaction is actually right, which is what I had to do here. Hopefully we know that a phosphate's charge is -3 and a nitrate's charge is +1. So a little typo here. There are 3 sodiums per 1 phosphate. So if you ever get really stuck, it's probably a little typo like that. That's your actual reactant. Let's try to balance this. So since this is our first one, I'll really just kind of go through it. Again, if you feel comfortable with this, pause this, just try all these examples, and then you can come back and watch me if you need, and if not, then you can skip ahead. So if you're just kind of getting used to this, I really recommend taking it slow, taking it one step at a time. Really just actually write out all your things you want to count. It just makes it's so easy to like get yourself mixed up, especially if you're new at this. So I would count how many of each thing I have on my left side of my arrow right now. I just have 1 calcium, 2 chlorines, 3 sodiums, and 1 phosphate. I'm going to line it up just so it's easier to keep track of. On this side I have 3 calciums, 1 chlorine, 1 sodium, and 2 phosphates. So what you'll do is you look at stuff on the right side and stuff on the left side, and any numbers that aren't matching up, you're going to try to fix them. So just pick one to start with. Let's do calcium. It's at the top. Why not, right? So I need to make this 1 into a 3. I want to make those match. And again, the only thing you can do is adding coefficients, so big numbers in front of compounds. So here's calcium. What number could I put in front to make it so I have 3 calciums? 3. So this means that I now have 3 calciums, but chlorine's also part of that compound. You're not allowed to break up the compounds at all. You're only allowed to add big numbers in the front. So it's also affecting my chlorines. I now have 6 chlorines. Okay. Well, we just messed up chlorine. Why don't we try that one? Chlorine is here. What can I multiply 1 by to make it 6? Now I have 6 of those, but I now also have 6 of those. Okay, let's do sodium. I have 3. What can I multiply 3 by to get 6? 2. And that also changes my number of phosphates. Bada bing, bada boom. If they all match, and sometimes like it can be tricky, like I really encourage you to actually cross these out, like keep track of all your numbers when you're first starting out, especially. Like it's so easy to get yourself confused. And if you do get confused, you probably miscounted at some point. Back it up, just start over. But that's that one. Let's try another one. So I'm going to have count my potassiums on both sides. I'm going to count my phosphates on both sides because they're on both sides. But I can't count the hydroxide as a unit because there's no hydroxide on the other side. So then I'm going to separately count my other hydrogens and oxygens. And if this is confusing for you, then you can do all the elements. I just think it's easier if you don't. So let's see what we got. We got 1. We got 1. We got 4. We got 1. And again, I'm just counting this oxygen because I am choosing to keep that as a unit. 3, 1, 2, 1. Okay. Feel like, okay, let's just start at the top. Potassium. I want it to be 3, and now it's 1. So if I put a 3 here, that'll change this to 3. I'm going to also add 2 more hydrogens, right? So now I got 3 plus 3, 6. I got 3 oxygens now. Okay. Now I gotta somehow fix my hydrogen and oxygen. So looking over here, if I want to change 2 into 6, I put a 3 here. That'll change this into 6. 2 times 3. And then I also have 3 oxygens in that compound. There you go. Sorry, I'm kind of going slow / not explaining things that well. If you want more help, just let me know or come on in anytime. Again, recommend pausing and trying on your own if you haven't yet. Just counting my starting numbers. And one at a time trying to fix things. If I want this to be a 2, I'm going to have to put a 2 there. That'll also change this to a 2. Okay. Now I have 2 chlorines on the left and 3 chlorines on the right. So I have to think about like what multiple do I have in common, like or least common multiple or whatever that's called. What could I multiply both sides by to get the same number on both sides? Or I'm gonna multiply by different numbers on both sides to get overall the same number. Not a good explanation, just watch. If I have 2 on this side and 3 on this side, the least common multiple of that, the lowest number that I could possibly have that is a multiple of both, is 6. So if I want to get 6 chlorines on this side, I'm going to put a 2 here. That's going to change this to 6 and change this to 2. And then, so I'm going to change this instead. I'm going to change it to a 6 so that those match. 6 and 6. So yeah, it is really just kind of a process, a lot of back and forth until you finally get them all to match. So I got chlorines to match now, but now my other ones are out of whack. Can I multiply 2? Let's do our hydrogens. Can I multiply 2 by something to get 6? I think maybe a 3 could get a 6 here. Okay, I got hydrogen and chlorine. And finally, I gotta somehow fix my aluminums. And if I pop a 2 there, then I have 2 aluminums on both sides. Okay, looking at this guy, you might recognize a few polyatomic ions, but there's no polyatomic ions that are on both sides. So I can't actually count the polyatomic ions as a unit because it's not a constant like on both sides. So instead I'm going to count each element on its own. Okay, and this, I haven't explicitly said this yet, but notice how we have we have oxygens in this compound and this compound, oxygens in this compound and this compound. So oxygens all over the place. It's gonna be not fun to balance the oxygens probably. So I would say that for the very last. Try to balance your other elements and just hope oxygen falls into place. So let's count this out. We got 1 hydrogen, 1 chlorine, 1, 2, 3, 4, plus 10, 14 oxygens right now on my left side, 4 phosphoruses on my left side, 3 hydrogens, 2 chlorines, 1 phosphorus, 4 plus 7 oxygens. So let's play with this. Let's see what we can do. So again, it's gonna probably be a lot of back and forth just because that's how it'd be. So you just pick one and try it, and it's gonna just keep going back and forth. Let's start at the bottom this time. Phosphorus, 4 and 1. If I want to get a 1 on, or 4 on this side, I'm gonna have to put a 4 here. That's going to change my phosphorus to 4. It's also going to affect my oxygens. So now I have 4 times 4, 16 oxygens, plus 7 oxygens. I now have 23 oxygens on my right side total. And I also have 3 times 4, 12 hydrogens on my right side right now. These numbers are already getting big, but you know, just be patient with yourself. Keep track of it as you change things. Cool. Hydrogen. Let's try it. We got 1 over here, and I need to make it 12. So I guess this is going to be a 12. And that's going to make it so I have 12 of these, 12 of these. And 12 times 4 of the oxygens plus the other 10 oxygens, 58 oxygens on my left side now, and 4 phosphoruses. Bear with it. It's getting better. I believe. I see it. I see the vision. Got hydrogens and phosphorus. Let's try chlorine. 2 times what is going to be 12? 6. So that's going to change this to 12. But it also makes it so we have 6 times 7 plus 4 times 4 oxygens, which, bada bing, bada boom, is actually 58. You did it. That's it. So yeah, kind of a lot to keep track of when they get more complicated with this, like this, but usually the answer's on the horizon. Just be patient and go back and forth as many times as you need. Okay. Stoichiometry. Again, hopefully this sounds very familiar. Stoichiometry is just a way of determining the proportions in which chemicals react. So that's just a lot of words for saying that it's like a way that we solve for how much product or reactant we're going to create or use up in a given situation. So dimensional analysis is all it really comes down to, or at least that's how I choose to do it. So, you know, we've pretty much already utilized this in other contexts, but we're just really clarifying, like, how do you figure this out? Something to keep in mind at, like, this level is that when I say I have, like, a reactant, if I have these reactants, I have this stuff on the left side of my reaction, and I'm trying to make certain products with my reaction. If I mix together some of this reactant and some of this reactant, in reality, most of the time you're going to actually use up one of those reactants faster than the other. Not a great picture for this example because in this one there's exactly the same number of needed moles of both things, but most of the time, like if I'm just mixing together a few grams of this reactant and a few grams of this reactant and I'm putting them in a flask and saying go, make my product for me, most of the time we're actually going to use up one of those reactants faster than the other based on the mole ratios and just how the reaction is going to work. So we have special terms for that. We have our limiting reactant. This is the reactant that runs out first, I'm going to say. And why that's important is if I ran out of one of my ingredients, I'm not able to make any more product. So the amount of limiting reactant I have limits the amount of product I'm able to produce. So, yeah. I also, on my channel, I have a even longer video of just about limiting reactants. So if you want to watch me do more stoichiometry, / get some more detail on this, you can always check that out. So limiting reactant, the thing that's going to run out first, the thing that's going to stop my reaction and force me to like only make a certain amount of product. So whichever one I have left over, that is my excess reactant. It's the one that is not used up during the reaction. So let's do a kind of more simple, just stoic question first, and then we'll do some limiting reactant problems after that. So just like at this level of chemistry, gotta realize that whenever you have a reaction, the first thing I want you to double check, always double check, is your reaction actually balanced? Do I have a balanced chemical reaction that I can use? Always double check. Sometimes they'll be nice and give you a balanced one, but sometimes they won't, and you always have to check. So let's take a look at this. I have silver, 2 chlorines, 1 chlorine, ruh-roh, not balanced. Gonna add a coefficient there. Now I have 2 chlorines, but I also now have 2 silvers. Now this is balanced. Again, if you wanna, if you're more new to that, please pause this, write it out on your own, make sure you can actually get that answer. But that is my balanced chemical equation. So how stoich works, I'm just gonna do a dimensional analysis problem. So let's see. What information do I have? I am going to add this much silver nitrate, that's this guy, to excess calcium chloride, this guy. So if they're nice to you, they'll tell you that one of them's in excess. And excess, again, that means we have like plenty of it. We have so much of it. We're not even going to use it all up. So that means that this excess reactant isn't actually important for how much product we're going to make. We're going to have plenty. We'll have as much as we need. The thing we're actually going to run out of is our silver nitrate. So if it tells you that something's in excess, then we don't need to factor this in. Okay. And then the question is asking for how many grams of silver chloride we're going to form. So, again, when I'm doing stoic, I like to write my goal over to the side so I remember where I'm going. And I like to do this all in just one big stoichiometry problem. You totally can do multiple steps if that makes more sense to you. But here's how I'm going to go about it. So, I'm going to start with a known. My known is the 3.50 grams of silver nitrate. And I'm just going to cancel things out until I get to my goal. If I want to talk about a different substance, so I'm comparing silver nitrate to silver chloride, different substances you always want to compare with moles. So I know that I'm going to want to change this into moles with my molar mass. And I'll save you the work of calculating that. Something like this. Now that I have it in moles, I'm able to use a mole-to-mole ratio from my reaction. So 2 moles of AgNO3 for every 2 moles of silver chloride. Still include the step. I'm always going to include the step. If it's a FRQ, they could totally grade you down for not including the step. I'm actually going to include my mole-to-mole ratio in here, even though it's a 1-to-1 essentially. I'm still going to show it. So now I have moles of silver chloride, and the question asks for grams of silver chloride, moles to grams, molar mass. and plug that in your calculator. Make sure you actually get this number. I would get that. Okay, so that would be like a straightforward question they could ask you. Just calculating, like translating between one substance to another, that is called stoichiometry. Now let's look at some more complicated ones. Here it tells you that you have this much HCl and this much zinc, and you have a reaction. And then the question is asking for how much volume of hydrogen gas gets produced from this reaction. So just like something I like to do, I always kind of like to keep track of my known information, especially if this is new to you. Like, it's so confusing when you're first starting out, like how to actually start these questions. So I like to write down all my known information and kind of organize it underneath my reaction. So I'm just going to do that off to the side. So I know that I have 50 milliliters of this. And I know that I have a 1 molar solution of this. I know that I have 2.35 grams of this. And I know that my question is asking about my hydrogen gas. Now, here's the kind of tricky part, or, like a common thing that at this level we have to consider. If they give you information about both reactants, if they don't tell you explicitly one of these is excess, you are going to need to figure out which one is limiting. Okay, so there's different strategies for this. The way that I am going to do this is I just do stoichiometry twice. I just do the same problem twice, but solve in regards to each reactant separately. And I'll show you what I mean in a second. Since we're here, just before we get started, since this is probably a new thing you might have not seen, it's asking for volume of gas. Two options here. Either you don't realize this trick I'm going to show you, and you solve for moles, and then you plug it into PV equals nRT. You could solve for the volume. Or a trick I briefly mentioned in class, it's on your equation sheet too if you forget. This temperature and this pressure, special name for it, it's called STP, standard temperature and pressure. And at STP, as it says on your equation sheet, any gas, any ideal gas, will have a volume of 22.4 liters per mole of gas. So we're going to use that in our calculations. So what I will do is, I'm so sorry I did not at all give you enough room to do this, but do your best. What I do is I assume each reactant is limiting separately. So I solve the problem twice. Once where I say, what if my only factor was the zinc? Once where I say, what if my only factor was the hydrochloric acid? And I do them separately. And then I see how much gas I could produce in each case. So this is very tedious. Go ahead and skip on forward if you would like. Starting with my known about zinc, using the molar mass of zinc to change it into grams because I know I'm going to want to compare it to a different substance using multiple ratio. From my balanced equation, there's 1 mole of zinc per 1 mole of H2 gas. And then from that little trick I just showed you, for every 1 mole of H2 gas, I know that there are 22.4 liters of gas. Multiply all across. If zinc was my limiting, I could make this many liters of H2. Okay, so that would be the situation if zinc was my limiting. So I just do that all again, but this time I'm only going to consider my other one. So I'm just going to do that again, but talking about my other factor. So this time I'm going to instead assume that my HCl is limiting. Probably would have been more efficient to just rewrite this all. Yep. Not thinking ahead very well. There we go. Okay, so starting with information about my HCl, I know that it has a 1 molar HCl concentration, which means 1 mole per liter. And I know that I had only 50 mils of it, so I'm actually just going to cancel that part out real quick. So I've canceled out my liters, but now I want to change my moles in the numerator into the hydrogen. So if I want to change moles of one thing into moles of another, I'm going to use my mole to mole ratio from the balanced equation. The coefficient in front of HCl is 2, the coefficient in front of H2 is 1. And from that SDP rule, for every 1 mole of H2, there are 22.4 liters of H2 gas. Multiply all across, and you would get this many liters of H2. So what information are we actually getting out of doing all that? So my goal was to figure out how much hydrogen gas could I actually make. I added both of these things to a reaction flask or whatever. Added both of them to my container. I said go, and I see how much product could I make. Mix them both together. What I kind of calculated here was saying like, okay, if I had plenty of the other thing, how much could I make with zinc? If I had plenty of zinc, how much could I make with hydrochloric acid? So what you actually use these numbers for, you look and see, okay, which one got me a smaller number? That's how much hydrogen gas you're gonna theoretically make. So your yield here would be this one. You never get the chance to make 0.8 liters of HCl. You only get the chance to make 0.56 liters of H2 because you ran out of HCl. So because I got a smaller number for HCl, HCl is our limiting reactant. Which means that this is the amount of H2 that could be made from the reaction. Okay, so let's think through how would this change if we had different conditions. What if I doubled the amount of zinc? So sometimes this is just like theoretical, like do in your head. But sometimes, like for me, I just prefer always just calculating it. Like I don't like really doing like too many math tricks in my head because I always mess them up. So personally, I'm gonna just calculate them. If you want to do little tricks to save yourself some time, you totally can. But I tend to just calculate this stuff. Okay, let's think about this. If I doubled the mass of zinc, if I doubled the amount of zinc, this is where the concept of limiting an excess reactant comes in. Zinc was my excess, right? I never got to use it all up. I never got to make this much hydrogen because I ran out of HCl. I only actually made this much hydrogen. Zinc was my excess. I had plenty of it already. So if I already have zinc left over and I just add twice as much of it, it's not going to change my yield. It's not going to change how much H2 I get to use because I already had excess of it. So this was my excess reactant. Which means that having more of it doesn't change our yield. Okay, let's consider that next one. So again, there are like little tricks to do this. I'm just gonna copy this down, redo the problem, but with this new number. So it's saying that I am doubling my moles, my volume of HCl. So instead of having 50, I'm gonna have 100 milliliters. And if I multiply all across, theoretically, I could make this much H2. And for each of these, it's saying like if you double the HCl, but everything else matched your original. So if I had this much zinc, but now I have 100 milliliters of the HCl. So what you're going to compare is, can you actually make this much hydrogen gas? And you're going to want to compare it to your original values. Notice now this number is bigger than this number. Now my HCl is excess. So I've added enough HCl that I'm able to react with all of my zinc to the point where I now have extra HCl. So I was able to actually react with all of my zinc. The amount of product we're now able to make is this. And I can't make this much because I don't have enough zinc to do that. Okay. So same thing, just gonna look back at my calculation and mess with it and see what result I get. Doubling my concentration. So instead of 1 molar, I'm gonna have 2 molar. Multiply all across, I'm gonna get this again. And same reasoning. I'm actually only gonna make the 0.8 liters because I now have an excess of my hydrochloric acid. Let's try that next problem. So again, we got a reaction. We are burning propane in a combustion reaction with oxygen. All combustion reactions always look like this. And we're getting these specific products. So if I gave myself enough space, I would probably write underneath both of my, underneath my equation, organize my information. I'll just kind of write it off to the side. I'll just make it really small. We have 41.1 grams of this. We have 41.1 grams of this. And the question is asking for what mass of CO2 are we going to make? So I have to figure out my grams of CO2. Okay. So again, there's different strategies. If you prefer a different one, that's totally fine. You could do it in multiple steps. I just like doing the problem twice. It's just like, it's the same every time if you just stick with doing it that way. You know, some of you might be able to do this, figure it out in your head which one's going to be limiting. But for me, when I just look at this, I'm like, oh, well, I got 44.1 of both. But they both have different molar masses and they both have different mole-to-mole ratios. So it's just more complicated just because it seems like, oh, we have the same amount of both. They're both going to use up at the same rate. No, they're going to be used at different rates. So that's why you really have to do these calculations or do some kind of math to figure out which one is going to be limiting. So I'm just going to run it back with that last one. I'm going to do one problem where I assume that my propane is limiting. And again, what I mean by limiting, that just means we're going to use all of it up, assuming that my 41 grams is going to limit the amount of product I made. I'm going to use all of that up. So just starting with this, and then I'm going to solve for my grams of CO2. So So 44.1 grams of C3H4. I'm comparing two substances. I'm always going to want to go to moles so that I can do that. So using its molar mass, which is this. And I know some of us, like, I know this gets tedious, it's a lot of writing, but I think it's important to really be clear about your units in your math, whether you're doing dimensional analysis or a different strategy, because like we're doing moles of different things, we're doing grams of different things, like it's so easy to mix them up if you're not being super clear to yourself of like what unit you're working with. To translate between my two substances, I'm going to use my mole to mole ratio from my balanced equation. Now I have moles of CO2 and the question asks for grams of CO2, so I can use my molar mass of CO2, which is this. Multiply all across, and if it was limited by my propane, I could make this much CO2. Okay, so that's one theoretical yield. Maybe I can make that much CO2. But let's take into account how much oxygen we have. We're in this sealed box with only a certain amount of oxygen. Let's see how much we could make if I used up all my oxygen. So again, solving for grams of CO2, starting with my grams of oxygen. Changing to moles so I can make comparisons. And using my balanced reaction, there are 5 moles of oxygen for every 3 moles of CO2. There's 1 mole of CO2. I can use its molar mass to solve for its grams. And if I solve this one, I can make this much CO2. So again, we have these two numbers. Like the theoretical amount I could make if I had plenty of oxygen, but I was relying on that amount of propane I was given, and the amount I could make if I had plenty of propane, but I have to rely on my amount of oxygen. This number is smaller. This is the amount we are theoretically going to make of CO2. I do not make this much CO2 because I have ran out of oxygen. My reaction was limited by the amount of oxygen I had. This is my theoretical yield. O2 is my limiting reactant. C3H8. It's excess. Of course, no one writes out full words in chemistry. Sometimes you'll see it written as that. Excess. Cool. Okay, again, let's do a little bit of like brain. Let's think through like how would adjusting my amounts of stuff affect my yield. Okay, it's saying if I had even more C3H8. Looking back up there, I already had plenty of C3H8. It was my excess reactant. Just adding more to the pile, it's not going to change the amount I actually make, my theoretical yield, because I have plenty of propane. More isn't going to change the fact that it's limited by my oxygen. So, again, excess reactant. No effect on my yield. Okay, what about the mass of oxygen? And again, you know, there's tricks to it. I'm just gonna straight up do the math just to assure myself, because sometimes there's weird cases like that previous one where you have to really consider all the things that are at play. Okay, let's see. It says that if I'm double the mass of O2, so instead I started with 88.2, what would my effect be? and I multiply across, and that is going to be 72.8 grams of CO2. So if it asks for the new yield, that would be the new yield. If it just asks to compare, like what effect that change would have, I could look back at here versus here. It increased by 2. So hopefully that's clear. So, very common multiple choice question. Again, you could probably figure that out in your head. Like, okay, we're doubling the limiting reactant. We're going to double our yields. The only thing you have to be careful about is making sure that it's not going to become limited by your other thing. But this is still a smaller number than this one. This is the amount we get to make. Our reaction was doubled. Our product was doubled. Okay, cool. One more, I just didn't know where else to throw this in. Percent yield, super simple. This is just if okay, so what we've been actually calculating, like the math we've been doing, is calculating how much I could make, like if everything went perfect, like just from the ratios, how much product could I make from this amount of reactant? Like just math, just ratios, how much could I possibly make? But in reality, a lot of reactions are more complicated than they appear. Science doesn't always want to work with us the way we wish it did. A lot of times we don't actually get to make all of that product. So there's something called an actual yield. And a theoretical yield. So an actual yield, that is like if you actually did the calculation, it would be the amount you produce. So this would need to be like some kind of lab data or some kind of given data. And our theoretical yield, that is like what we calculated with stoichiometry. Okay. So theoretical yield, all the stuff we've been calculating so far is our theoretical yield. This was 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 our theoretical yield. So if you just calculate it, that is theoretically how much we can make. But then in reality, we usually don't get to make that much. Neat. So percent yield, that's just a way of comparing those two things. How effective was your reaction is basically what this number tells you. So you just throw actual over theoretical and multiply by 100 because it's a percent. So usually pretty simple. I'll start throwing these on as part of like our labs going forward. So if you're given a problem like this, 3.5 silver nitrate is stirred into excess calcium chloride, but you only get to form 1.5 grams of silver chloride. Now, if this was like a new reaction you've never seen before, then you'd have to like do the stoichiometry, figure this out, figure out what your theoretical yield is. But luckily we already did that. It was nice. So this is the same reaction as what you had up here. Same starting amount with 3.50 grams of silver nitrate, and we figured out that we could make this much silver chloride. So that is our theoretical yield that we calculated. Again, if you hadn't done that yet, then you'd have to do that first. Or if a problem asks for a theoretical yield, you just are doing a stoichiometry problem. So my actual, it says that I only got to make this many grams of silver chloride. Let's pretend that I said that so that it can be 3 sig figs. I just made this up. Let's pretend I made that much. And then I get my theoretical yield, which was 2.95 grams of superchloride. Same units on top and bottom, so those are canceling out. This is just a percent with no units, or the units are percent, due to math, and that is a 50.8% yield. Okay, so something, like maybe you had an impure sample, or maybe you dropped some of your reagent, or maybe the conditions just weren't working, or maybe there were side reactions. There's lots that can go wrong to cause your actual to not match your theoretical, but not a super efficient one. Okay, representations of reactions. So like, how are we going to actually like visually show or communicate that a reaction has happened? How can we represent the different parts of a reaction? There's two main ways. One of them we've already learned. We can do a reaction equation. So that's all the ones we've been doing. A chemical reaction equation. Or we could do a particulate model. They sure do love giving you little boxes with a bunch of circles in them. So these are both ways of representing reactions. And you know, if you have the equation, you could be able to draw it, be able to communicate the reaction in a picture. Or if you were given the picture, you could translate it into a reaction. So you should be able to go in between these two things and communicate about your reactions. So let's look at an example. I have my left side of the arrow, and I have my right side of the arrow. So just like in a reaction, this is communicating that I have my reactants and my products. And let's look at like how the stuff in the box looks different on both sides of the arrows and see if we can answer these questions. Pause and try it on your own first. Is this a physical or chemical reaction? So think back to what physical and chemical means. Physical would be if there was like a phase change, or if the substances look the same in both boxes, but maybe something about them has kind of changed. Maybe they've spread out, something like that. If it's a chemical change, we've formed new substances. So hopefully when you're looking at this, you notice these guys. In this box, I have the H2 and the N2, just 2 black dots and 2 white dots. But here, this is showing new molecules. The N is connected to the H instead of having 2 separate things. So I have made a completely new substance. I have new particles. So that's how I know that this is a chemical reaction, because I see that new compounds are made. Okay, let's see if we can make a reaction equation out of this. So let's kind of just walk through this and talk about like how we communicate that clearly. So looking at my reactants, I have N2 and H2. And it even says it in the key. But looking at the box, I want to always include my states if I know them. So I can see that these particles are all spread out, and as we've talked about, that shows that these are gases. So I have N2 gas and H2 gas. And then my product. So what is the thing that is the new thing that has been produced by that? That is going to be my new product right here. And matter can't be created or destroyed. It has to be made out of the same elements that I started with. So that white circle must be an N, and those black circles must be H's. So my product is ammonia NH3. And again, those are spread out. They're filling up the space. So I could say that this is a gas. I always want to have a balanced chemical equation if I want to make it complete. So I think that might be a little bit confusing if you're looking at the pictures. Maybe you're tempted to go 3, 3, 2. Maybe you even wanted to do the nitrogens over here. But no, we always want our balanced equation to represent the ratios that the reaction happens in. We always want reduced numbers here. So honestly, you can just balance it the old-fashioned way, or you can look at the picture. For every 2 of these I produced, comparing my picture, I can see that I used up all 3 of my H2s, and I only used up 1 of my N2s. So that's what this is showing. I had 3 N2s, and I still have 2 N2s. It's not saying I produced N2, it's showing that I didn't use these ones up. So what that is actually communicating to me is that I have an excess and a limiting. I have a limiting amount of H2 because I used it all up, and I have an excess amount of N2 because I can see that it's still left over. It's part of my products. Or, it looks left over as part of my products. Okay, so hopefully that's pretty straightforward. Just wanted to clarify that. Okay, last thing I wanted to throw in here. We will go into more detail on all of these, especially these ones, in our future sections. But just to give you kind of an overview, a little like reference page for these. I know in like different chemistry classes, there's a bunch of different names for different reactions, but here are the categories that we use in AP Chem. Here's the like names of reactions. So like common multiple choice question is having a reaction equation and being like, which type of reaction is it? And you have to identify it as combustion, precipitation, redox, or acid base. And again, we'll get more on those other ones, especially acid base and redox. So, we'll get to it. But combustion, hopefully that sounds very familiar. This is always an organic fuel combusting with oxygen gas. This one, it like just always kind of looks the same. Organic means made of carbon mostly, and then hydrogen or oxygen or nitrogen. So you'll have something that kind of looks like this. Some amount of hydrogen, some amount of carbon, maybe some oxygen in there, maybe some nitrogen in there, but always a whole bunch of carbon. And then it will be with oxygen, always as a reactant. And then it's always going to produce CO2 and water and energy. Now the energy part, not necessarily written, so don't let that throw you off. But just so you know, these always produce energy. We'll talk more about that when we talk about exothermic and endothermic. So these ones, it's just like if you see a bunch of carbon and you see these 2 very specific products and you see this oxygen, it is combustion. Precipitation. So this implies that you formed a precipitate. And to clarify, a precipitate, that is a new insoluble ionic product So the way you recognize it is look for a new, like an ionic solid, or yeah. And whenever I say salt, that always just means ionic. So you have some kind of ionic product that is insoluble. We'll learn about net ionics in class tomorrow, whenever you're watching this. So they also have a very distinct net ionic. We'll see that in class as well. And with a lab that we're going to do next week. Okay, redox. Oxidation reduction. Again, we'll spend much more time on this, but it is a reaction, is defined by a reaction where electrons are transferred between species. So one thing is going to be losing electrons, the other thing is going to be gaining electrons. This is not the same as an ionic bond. I want to be super clear about that. It's about like the electrons actually moving as part of the reaction, we're going to change the amount of electrons that a element or something has in a in a molecule usually. Like, so usually you'll have metals. Yeah, I guess there are actually lots of different types, so, you know, we'll see them. And really the thing to focus on for this, for actually recognizing them, there's these things called oxidation numbers, and you're going to learn how to recognize them. And if there is a change in oxidation number, for an element as part of the reaction, so as a reactant versus a product, that's what you're going to be looking for. Again, we'll learn about that, but this is your telltale sign. By definition, if there is a change in oxidation number, it is a redox reaction. Acid-base, the way we will define this is by proton transfer. So the way you're going to recognize it is if a proton, and the way we define that is a hydrogen ion, because it doesn't have an electron, so it's just a proton. So if you see an H move around, one thing as a reactant had an H, and then one thing as a reactant didn't have an H, and then as products, that other thing now has that H. If the proton has been transferred, from an acid to a base, and we'll learn about recognizing those in the future. This is just supposed to be a reference for you. There's a different type, so this is like any acid base, like an acid base reaction is this. And then there's a specific like subtype that we also see sometimes, a neutralization reaction. Again, we'll talk more about it, but that one always has the same format. It's always an acid plus a base. And the real important thing to look out for this one is that you are making a salt and water as your products. Again, when I say salt, that just means ionic compound. So this is how we recognize this one, looking for those two specific products, salt and water. Okay, so that's just a little reference sheet for you. I think it will be a more valuable resource as you learn more about these reactions, but just wanted to give you a big picture before we get more detail on them moving forward. And yeah, that's it. Thanks for sticking it out, and let me know if you have any questions.